Right now, somewhere out there, a 400-ton train is moving through a railway network, and as far as the system watching it is concerned, it doesn't exist. The signals ahead show green, the track shows clear, and another passenger train, right behind it, has just been given the same green signal to enter that very same track. There's a difference between a train that's lost and a train that's invisible. A lost train can eventually be found, parked on the wrong siding, buried in paperwork, sitting somewhere nobody thought to check. Sooner or later, someone finds it. But this train isn't hidden anywhere. It isn't diverted, parked, or forgotten. It's moving at full speed, right where it's supposed to be. The problem is that the system deciding whether the track ahead is safe has no idea it exists. This isn't a movie plot. Every year, somewhere in the world, a real train disappears from the system meant to track it, or the opposite happens, and a system locks up an entire main line chasing a train that was never there at all. Two very different failures, but they both begin with exactly the same question. How does a railway know a train is there in the first place? How does a piece of 19th century electrical wiring end up deciding whether a modern high-speed train gets a green signal? Why does the exact same system built to make railways safer sometimes make a train invisible instead? And what happens when the fix for one blind spot quietly creates another one? You'd assume railways track trains the way your phone tracks you. GPS, a live dot on a map. Mostly they don't. Most of the world's railway network still runs on something far older and far simpler: electricity, running straight through the rails themselves. The two rails of a track section are wired into a low-voltage circuit. Current runs down one rail, into a relay, and back along the other. No train, no problem. Current flows freely. The relay stays powered. The signal shows clear. But when a train rolls onto that section, its steel wheels and axles bridge the two rails together, creating a much easier path for the current than the relay itself. The current takes the shortcut through the train instead. The relay drops. The signal turns red. This is called a track circuit. It depends on clean metal touching clean metal, but rails sit outdoors year-round. What happens when the weather gets involved? Rust builds on it. Rain sits on it. In autumn, crushed leaves bond to the railhead and bake into something closer to a thin coat of black lacquer than dirt. All three do the same thing electrically. They add resistance between the wheel and the rail. The electrical short circuit the system depends on becomes weak and unstable. Instead of a clear signal, the system begins to flicker. Sometimes it detects the train. Sometimes it doesn't. And if that electrical contact stays too weak for too long, the system can show a section as clear while a real train is sitting inside it. A false clear like that can have catastrophic consequences. That exact failure mode, trackside equipment quietly deciding a section is empty when it isn't, is not hypothetical. In July 2011, near Wenzhou in China, lightning struck a trackside signal control unit on a high-speed line. The strike blew a fuse inside it. That unit was supposed to fail toward danger no matter what broke inside it. Instead, it failed the other way. It reported the section as unoccupied, so the signal stayed green. A train was stopped on the track ahead. The train behind it was cleared to proceed. 40 people died. But that's not the ghost railway engineers deal with most often. The far more common type of ghost train runs in the opposite direction. A section shows occupied when there's nothing there at all. But what creates a train that isn't there at all? After the train that caused the flickering signal has actually left, there's a design principle deciding what happens next: fail-safe logic. If a system is ever in doubt about whether a section is truly clear, it's built to assume the dangerous case: still occupied. So if the relay was chattering as the train left, or if damp ballast is quietly leaking current between the rails on its own, the system won't clear the section. It gets stuck. Red signals, stopped traffic, engineers walking miles of empty track looking for a train that's long gone. This isn't a design flaw exactly. It's the same caution that's meant to prevent another Wenzhou. So why wasn't this problem solved by simply replacing track circuits altogether? Track circuits aren't the only way railways detect trains. Many railways now use a completely different approach. It's called an axle counter. Instead of using electricity flowing through the rails, it uses electronic sensors beside the track. These sensors sit at the entry and exit of a section and simply count wheel sets. How many wheel sets went in? How many came out? Match the numbers. The section is clear. No contact resistance, no rust, no leaf residue to worry about. On paper, it's the fix. But swapping the vulnerability doesn't remove it. It just relocates it. Axle counters can be thrown off by electrical interference, a nearby lightning strike, a badly shielded motor, or even wheel slip in wet or icy conditions. When an axle counter loses confidence in its own count, it doesn't quietly sort itself out once the discrepancy resolves. It locks. The section stays marked occupied, sometimes for hours, until someone physically walks the track to confirm it's empty and manually resets the counter by hand. Which raises an uncomfortable question. Why do ghost trains appear at all? If you're finding this hidden side of the railway world as fascinating as I do, that's exactly what Blind Spot is about. Take a second to subscribe. It's the easiest way to make sure you don't miss the next Blind Spot. Ghost trains aren't ghosts at all. They don't appear because the railway suddenly loses control. They appear because the system is forced to make a decision when the evidence is incomplete. Sometimes that means a real train becomes invisible. Sometimes it means a train that doesn't exist refuses to disappear. Both are the price of asking a century-old signaling philosophy to answer a simple question with absolute certainty. Is this track safe? These ghosts are usually created by things so ordinary that most passengers never notice them. A layer of wet leaves, a wheel that slips for a fraction of a second, a damaged cable. None of them look dangerous on their own. But inside a signaling system built to choose caution over certainty, they can create trains that vanish, trains that never existed, and delays that puzzle thousands of passengers every single day. The next time your train stops unexpectedly between stations, and the announcement calls it a signaling fault, you're not automatically in danger. There's a good chance you're just sitting inside a 100-year-old electrical circuit, having a very cautious disagreement with a patch of wet leaves. Managing a ghost train is one thing. Managing what happens after a real collision is a completely different system with its own rules and its own chain of command. The secret protocol behind train crash cleanups. That's the investigation waiting for you next.